So in this lecture, we're going to just briefly cover units of measurement, significant figures, scientific notation, little things like that. And starting off with units. So science and physics is basically a science of measurement. We're measuring things. We're going to be quantitative about this. It's one of the big utilities of science is you can predict things, but you need units to do that. You can't say, all right, I'm going to launch this ball and it's going to land five. You need five what? Meters, kilometers. You need some sort of unit for any type of measurement we're requiring. Now, in science, the units we use are the SI units or the System International Unit. Um, these are a set of units that are agreed upon. Um, there's actually treaties between countries on what these units are and how they're defined. And there are seven base units in this unit system. They are the kilogram for mass, the meter for distance, the second for time, the ampere for current, Kelvin for temperature, mole for the amount of a substance, and the candela for the luminosity of a substance. We're not going to be using all of those in this class because we won't deal with some of those quantities. But we will be dealing with a few of them. Some of the big ones that we've already touched on is the unit of time, which is the second. It's abbreviated with S. You're probably very familiar with this. You know how to tell time. But the definition for a second is 1 second is defined as the time required for that huge number of oscillations of a radio wave absorbed by a cesium-133 atom in a certain transition. You are not expected to understand any of the atomic physics involved in that or the timekeeping, but there is a rigorous definition of what the second is, and not only that, how to measure it. Likewise, the meter, abbreviated M, is defined as the distance traveled by light in a vacuum during one, essentially 3 times 10 to the 8 of a second. So you need the second to kind of help define the meter. Again, a very rigorous definition. There's ways, there's in these treaties, there's something called the maison pratique, which is an agreed upon way to measure a second in a lab and to measure a meter in a lab or any of these units. And there are these treaties are agreed upon in between countries so that when a business in America, say, wants to sell, I don't know, a million kilograms of apples or something to China, they've measured a kilogram in using a calibrated scale that is calibrated by our national lab, the National Institute of Standards and Technology, the lab that's in charge of these standards in America. It's part of the Department of Commerce, and they have really expensive equipment. They have a lot of scientists working on what these definitions are and how to properly measure them, and then disseminate those standards and calibrate measurement instruments. And it turns out that if you've got a calibrated instrument from NIST, that's traceable back to this maison pratique and the agreed upon definitions. So when you're doing business with another country, they're not tipping the scales and they're not selling you, I don't know, 10 kilograms of whatever when really it's only 9.5 because their kilograms different. Um, NIST is also actually, I'm going to nerd out a bit here. These national labs are ridiculous in how accurate they can measure things like time. I think the state of the art clock at NIST can measure the second accurate to 18 decimal points. So that means if they're measuring time and they measure a second, they know that that is 1 second exactly up until the 18th decimal point in that, which is obscene. If you've ever seen the movie Interstellar, there's this scene where these astronauts land on a planet that has a strong gravitational field, so time slows down for them relative to their partner who's up in the satellite off the planet. And when they go back, that person's aged much more than them. It turns out there's some actual real physics in this. Time does slow down when you're in a stronger gravitational field. And the NIST clocks are accurate enough to measure the difference that the difference in the speed of time, 1 foot in due to 1 foot in the difference in height. The closer you are to Earth, the stronger the gravity is. And if you are 1 foot closer to Earth, then the NIST clocks can measure how much time difference, how much slower time ticks because of that. That means they technically have the precision to measure how much older your feet are than your head. And anyway, this is beyond the scope of the course, but I always found it just ridiculously interesting how well they could measure things like the second. Another good thing about this SI units is they're mod 10. So they basically work on powers of 10. All the conversions are going to amount to multiplying by some 10 to the whatever. It also makes it really easy to discuss different scales. So if you think of, say, distance, if you want to discuss, the distance from here to LA using SI units, well, the meter is pretty inconvenient because it's going to be several thousands of meters. But we can just convert and use kilometers, which is 10 to the 3. Each kilometer is 10 to the 3 meters, and describe that distance in kilometers. Whereas if we wanted to describe, say, the size of the transistors in your computers or your phones, those are much smaller. We'd be using nanometers or 10 to the minus 9 meters. So we have this whole system of prefixes that are agreed upon. Giga is 10 to the 9, mega is 10 to the 6, kilo is 10 to the 3, centi is 10 to the negative 2, milli 10 to the minus 3, micro 10 to the minus 6, nano 10 to the minus 9. There's also pico, femto, zepto. There's a bunch of them. The ones here are the more commonly used ones, but it makes using these units at different scales pretty convenient. So as great as the SI units are, unfortunately, not everything is given to us in those units. So one of the things we're going to have to be good at is converting units from various different systems of measurements. So just we're going to work through a few examples of this, and it all boils down to, at its simplest level, essentially multiplying your quantity by 1 is the way I like to think about it. So let's take a common sort of unit that we're probably very familiar with. The unit of speed on highway signs and that, and in cars, miles per hour. So let's say we're driving at 60 miles per hour, or written another way, 60 miles per hour. Right? And if we want to convert, so our goal is to convert this number, this unit, into our SI units. And the SI unit for speed, well, it's change in distance, so it's going to be meters over time. So those two units are meters and seconds. So it's going to be meters over second is what we're trying to convert this to. Now, as I mentioned, I like to think of this as just multiplying by 1. So if we look at this, we just have to figure out, what the right way of writing that 1 is. So we have to get miles into meters somehow, right? And in the textbook or online, you can look up these conversion factors, and one of the ones you'll see is that 1 mile is equal to 1.609 kilometers, right? Which essentially means I can write 1 is equal to 1.609 kilometers divided by 1 mile. Just divide both sides of this equivalence by 1 mile, and that's what we get. So if I can use that, and since 60 miles per hour, if I take that number I'm trying to convert and just multiply it by 1, it won't change it. So kilometers per mile. I can perform this, and I'm going to get cancellations. And if I do that, this means that 60 miles per hour is equivalent to, let me get my 96.5 4 kilometers per hour, right? I'm still not at the meters per second though, I need another thing to multiply. I know 1 kilometer is 1,000 meters, so I can multiply by 1,000 meters divided by 1 kilometer. So if I take that and multiply it by 1,000 meters, 1 kilometer, again, I can cancel those units, and this ends up being 9,650 meters per hour. And I've now got meters where I want it. So now I have to convert this hours into seconds. And again, we're just going to look up some conversion factor. You're probably all comfortable with there are 60 minutes in an hour. So I can write 1 hour divided by 60 minutes is equal to 1. And I can take this and multiply by that. 1 hour over 60 minutes. And again, I can cancel those units. And this gives me, sorry, what? Where am I? 1609 meters per minute. And the final one, it's going to look very similar to this. If I take 1 minute, it's equal to 60 seconds. So I can create my one again. And if I multiply, 1 minute divided by 60 seconds, that minute and that minute cancel. And this ends up being 26.81 meters per second is that original speed that we calculated. So again, I can convert any unit into any other unit just by figuring out ways to write 1 and multiplying that. Multiplying anything by 1 doesn't really change it. So you can do that just by carrying units. You know, there's quicker ways to do this. You know, we also know that this is equal to 36,000 seconds. You know, there's 60 seconds for every minute. So you can create your ones however you want. But that's essentially all we're doing. And I encourage you to write it out in full form like this because you can, doing this brute force crossing out of units will automatically correct if you messed up. I don't know whether to multiply by 60 or divide by 60. Writing out, say, the full 1 is equal to 1 hour per 60 minutes and then multiplying by it, you won't be able to cross off the units if you've written it wrong, and it'll sort of alert you to that mistake. So the last thing that I want to discuss in this video, we've looked at units and how to convert them, is the concept of significant figures, right? So what are significant figures? Well, the gist is, the way I like to think about it being an experimental physicist, is essentially don't lie, right? You have certain values and numbers that we're using, and we only know them to a certain precision, right? If you're measuring the distance from your house to your neighbor's house and you have a meter stick and that's all you have, it has no smaller deviations on it, you can only measure that accurate to a meter, right? So if you say the distance is, 10.568 meters, those last few digits don't really have any meaning because you couldn't measure them that accurately. So significant digits are kind of an important thing to keep our calculations in that honest. Let's see how this works, right? So let's say we have, we'll just draw a motion diagram. I have two objects going here. One, x1, we'll say is at 3.72 meters. It's an object just moving to the right, like that, with some velocity v1. And x2 is at, we'll say, 10.5 meters. And the time between these two images took 1.1 seconds, all right? And we want to calculate v1, what that v1 is. So we know from previous videos and what we've learned that the velocity is defined as the change in position with respect to the change in time. So this would be 3.72 meters. Correct that. It would be 10.5 meters, final position, minus the initial position, 3.72 meters. divided by that 1.1 second, right? And again, let's just assume that we've measured these positions accurate to those precisions, right? We can measure to the centimeter these twos in distance, and we have a watch that's accurate to 1/10 of a second, right? So if I continue this calculation, this ends up just being, if I enter it into my calculator, it's going to spit out 6.16364 meters per second is the velocity of that thing. But again, these numbers don't all mean anything, right? This would mean I could measure accurate to say micrometers and microseconds, the fifth decimal point of my thing, and I can't. So a lot of these numbers are meaningless. So the way we deal with significant figures is we look at how many significant figures were there in the numbers we used, right? And this x1 position number had 3 significant digits. There was 3 numbers with meaning sort of in this. This x2, again, 3. And this delta t had 2 numbers, just 1.1. And we look at what sort of think of it as like the weakest link in this calculation determines the number of significant digits. So this calculation has 2 sig figs. That's the way I'd write it, significant figures. So what that means is I can only report this number honestly using 2 digits, would be 6 point, the next digit's what matters. But this would be rounded to a 2 because the next digit's there. So the answer would have been 6.2 meters per second reported to 2 significant figures because the smallest amount of significant figures of the numbers that went into that calculation was 2. And again, the whole idea behind this is those are the ones that have meaning. We report, when we make measurements or have numbers, we report them to a certain number level of precision. And if we report numbers based on that, we can't increase our precision by doing some calculation. We would have to do another measurement or get more info somehow. So if we report more significant digits than we had to make our calculation, we're kind of claiming we know more than we actually do. That's the gist behind significant figures. I'm sure as you go through other science classes, this science class labs and that, you'll encounter this more when you treat uncertainties and different things like that. Anyway, that's all for today. Next class or next lecture, I guess we'll go through graphical representations of motion and how to think about motion that way.